Fine. Consider this system. Okay, there's a box placed on a rough horizontal surface. The block is in equilibrium. One of you tell me what all forces act on this block. Assume its mass is m, so what all forces act on it?
Weight and normal.
mg. Mg and normal force, correct. Now, every particle of an object has weight. Okay, and if g is uniform, acceleration due to gravity is uniform, we have proved that, or we have derived that weight can be assumed to be acting through the center of mass if g is uniform. Okay, let me draw it properly. The other force acting on it is the normal force. Where does normal force act on this object? Anyone? Where does normal force act on this object?
At the point of contact.
How many points of contact does this object have with the ground? Is there only one point of contact?
No, sir.
There are infinite number of points of contact. Okay. And do you think the box will be pressing the ground at all those points or only a few points? I'm asking this generally, any of you can answer.
All the points.
All points. Okay. So basically, normal force on this box, okay, acts at multiple points. But we can tell for sure that it will act in the upward direction because normal force has to be perpendicular to the surface of contact. Surface of contact is horizontal, so normal force must act vertical like this. That much we can say. But there will be infinite points at which normal forces will be acting. Okay. Now, if you want to replace all of them with a single vector, can it be done? Like till now, we had
Yes,
been
sir.
doing that. We had always shown normal force as one vector, but we never thought about the different points on which it acts and how to replace all of them with a single vector. Okay. Someone said yes. Okay. See, there are many normal forces acting at different points of contact. The resultant of all those black vectors that I have drawn, all the normal forces, will be in the upward direction because all these normal forces are in upward direction. Resultant will be upward. And that resultant must be balancing mg. So the combined effect of all these small vectors that we considered, all these normal forces that we considered, should be in the upward direction. That much we can say for sure. Okay. And in magnitude, it should balance mg. That is also okay. What about the exact line of action of normal force? Should it be same as the line of action of mg or will it be different? Aishwarya, you tell. What can you say about the line of action of normal force? Rishi?
Same
Huh. Okay. Fine. See, this box is in equilibrium. Equilibrium means net force is 0 and net torque is also 0. For net torque to be 0, both forces must have the same line of action. If their lines of action are not same, then they will produce non-zero torque about some axis. Okay, so we can tell for sure from based on the fact that the box is in equilibrium, we can tell for sure that the normal force's line of action must be same as that of mg's line of action. Okay, hope this is clear to all of you. Now let's consider another situation. Now the floor here is rough. Assume this is a heavy box. Okay, and let's say you're applying a horizontal force this way, close to or somewhere in the upper on the upper side of the box. You apply a force like this. Now, since it's a rough surface, it's possible that the box will still be in equilibrium even when you apply a force this way. So let's say we have applied a force like this, but the box is found to be in equilibrium. Okay. Rishi, tell me what other forces act on this box?
Sir, friction.
Friction, in which direction will it act?
Opposite to the force acting.
Okay. This box will have a tendency to slide to the right. So friction will act to the left. Correct. What other forces act? The force we are applying, the weight, friction, what other forces act? Anyone?
Normal force.
Normal force. Okay. Now, normal force will act on the base. Friction is also a contact force. It will also act on the base itself. And friction acts to the left. Okay. So when seen from this side or this angle, we can tell for sure that friction's line of action will be like this to the left. Okay. Let me name it small f. So capital F is the external force that we are applying. Small f will be acting. And in fact, small f should balance capital F. That is the only way the box can be prevented from sliding. Okay. In addition to these, there will be normal force acting on the box. And normal force acts everywhere on the base. Now you all tell me, do you think the normal force which acts on the base will be uniformly distributed, or will it favor any one side of the box? Like in the previous case, the line of action of normal was passing through the center, means it was uniformly distributed. In this case also, do you think it will still be uniformly distributed or not? Vanilla, what do you say? Anyone else? Do you think normal force acting on the base will be uniformly distributed, or there'll be more normal force on one side of the base, less normal force on the other side?
Sir, I think it will be
Okay, Vanilla is saying it will be uniform. Any other ideas, anyone? Okay, if the normal force is uniformly distributed, as in the previous case, okay, I'll just copy these vectors. If normal force on the base is uniformly distributed like this, then the line of action of normal force should be same as line of action of mg. So the normal force must be acting like this through the center. Okay, if the normal force on the base is uniformly distributed, its line of action must be this. Okay. Now we know we see that the box is in equilibrium. Consider an axis through the center of the box. Vanilla, tell me, which of these forces produce torque about this axis?
sir friction and the force.
Capital F and friction. Capital F produces torque about this axis in which sense?
Clockwise, sir.
Clockwise. Okay, R cross F. Now line of action of force, or you can see the point of application of the force. R from the axis will be this way and then turn in the direction of F. R cross F, clockwise sense. Okay. Rishi, you tell me, in which sense does friction create a torque on this box about the center?
Anti-clockwise, sir.
How did you conclude it is anti-clockwise? Okay. It
Sir,
is
no,
also
1 second.
it,
It
huh,
it's normal to the point of application, so
no,
I
wait,
think it should
wait.
be clockwise only.
What is normal to the point of application?
Torque, sir.
Nothing can be normal to a point. You can draw normal to line, you can draw normal to surface, you can never draw normal to a point. Wait. You need R cross F. Okay. You know friction acts on the base and it acts to the left. So from the axis, you take the position vector to any point on the base and turn in the direction of friction. R cross F is going to be clockwise. That is how you decide the sense of torque. Okay. So friction also creates a clockwise torque in this case. Now friction's torque is clockwise. The applied force capital F is creating a clockwise torque. How can the box be in equilibrium then? But we find that it is in equilibrium. Okay, in a real life situation, it's possible, no? On a heavy box, like you take the refrigerator in your house, you apply a gentle force at the top of the refrigerator, it won't fall, it won't move. That means it's in equilibrium. Friction will be acting on it. There should be something opposing your force. But what is opposing the torque here? The line of action of applied force is not passing through the center. Any idea, anyone? Okay, listen carefully. When we apply a force like this, suppose friction is sufficient to prevent slipping. So no slipping occurs. But there's something else that can happen. You can experience this in daily life also. Just a moment, I'll try to show you. You consider this water bottle. It is in equilibrium. Okay, my hand is at rest. The bottle is at rest on my hand. Okay. Now, if I apply a gentle force at the top, okay, observe what happens. You can see the base here. Okay, it is resting on my palm. If I apply a force somewhere here, observe what happens. The bottle doesn't slide forward. It rotates, tilts. Okay, this is what we call toppling. The base doesn't skid forward like this. The base stays where it is, but because of the force that I'm applying, one side of the base has a tendency to lose contact. The other side will get pressed harder onto my hand actually. Okay, when I don't apply that force at the top, normal force will be uniformly distributed on my palm. Okay, or this bottle, it has these supports here. Normal force will be uniformly distributed on all 5 of them. But when I start applying a force this way, see what happens. One side of the base is losing contact, the other side presses harder onto my hand. So when I apply a force like this, what happens? Normal force on this side will decrease. It is losing contact, no? So normal force will become 0. When there's no contact, there cannot be a normal force on those points. So when I apply a force this way, the points on this side, okay, the points on this side of the bottle experience more normal force. The points on this side experience less normal force. They are losing contact. In fact, when they lose contact, the normal force on these points becomes 0 altogether. But when I gently apply a force also, I can feel this side becoming lighter, the other side becoming heavier. Okay. So this is what we mean by shift in normal. So same thing happens with this box also. When we apply a force at the top, it has a tendency to rotate clockwise, but it does not rotate. Means there should be something producing an anti-clockwise torque. And we have just seen that the normal forces on this side will be lesser. Okay, you can see vectors are getting adjusted there. And normal force on the other side will be stronger. So this is exactly what happens. And the line of action of normal will no longer pass through the center. Obviously, you can see how the vectors are distributed. The stronger vectors are on the right side. Okay. So the small vectors create clockwise torque. The stronger vectors create anti-clockwise torque, and that will dominate. Therefore, the net torque due to normal force here should be anti-clockwise. And for that to happen, normal cannot act through the center. It will be somewhat like this. N is still equal to mg. Because for vertical equilibrium, something should balance its weight. Normal force is the only thing which can balance its weight. So N is still equal to mg, but its line of action is not through the center. You can assume its line of action has shifted by some distance x. You can even calculate x. How? Just write net torque equal to 0. Clockwise torque is equal to anti-clockwise torque. You can even tell how much is the shift in normal. Is the idea clear to all of you? Aishwarya, Rishi, Vanilla, did you all understand?
Yes.
Okay. I want you all to write the equations now. See, net force equal to 0, we have already done. Sorry. We know friction is equal to capital F. We know normal force is equal to mg. That part is done. Write net torque equal to 0 now. So what I want you to write is, on the left hand side, write the expression for clockwise torque. On the right hand side, write expression for anti-clockwise torque. Balance them and get the distance x. Find out by what distance normal force shifts. Do this all of you. I'll give you 2 minutes. You can type your answer in chat. Answer should be in terms of capital F, maybe mg. And yeah, you need the dimensions of this box. Assume it's a cube of side A. Okay. So x will be in terms of F, mg, and A. Try. Okay. I got 2 answers as FA divided by mg. I think that is correct only. Capital F creates a clockwise torque. Assume it acts at the topmost point. Okay. I should have clearly specified that. Fine. Assume it acts at the topmost point horizontally. Then its line of action is at a distance a by 2 from the axis. Friction's line of action is also at a distance a by 2 from the axis. So the torques produced by them will be capital F a by 2 plus small f a by 2. Both are producing clockwise torques. mg's line of action passes through the center. It cannot produce a torque. Normal force's line of action has shifted by a distance x. Therefore, torque produced by normal force will be normal force multiplied with x. Now we'll substitute small f is same as capital F and normal force is same as mg. Then left hand side becomes capital F A. Okay, 2 times of capital F A by 2. That's simply Fa. Right hand side becomes normal force is mg, mgx. Therefore, x is equal to Fa by mg. So you can even tell by what distance the line of action of normal force has shifted. Okay, hope this is clear to all of you. Now see, in this situation itself, okay, like I showed you with the water bottle, up to a certain amount of force, the bottle's base won't rise. Okay, but when the force exceeds a certain value, the bottle cannot stay in equilibrium anymore. It may not slide forward, but it definitely rotates. Okay, it may not, like its base may not skid in the forward direction. So friction is sufficient to prevent sliding, but rotation cannot be prevented. When does that happen? You know, you have to go on increasing the force to make the box or bottle topple. Okay, fall over. Now, what happens as you increase this force is, to prevent sliding, friction will increase itself. Okay, assume it is all within limiting friction. Okay, assume friction is sufficient. Assume the surfaces are rough enough. So as you increase the force that you are applying, friction will increase itself. Okay. Now, if the force we are applying is increasing and friction is increasing, the clockwise torque is increasing. Then to keep the box in equilibrium, or for the box to be in equilibrium, anti-clockwise torque should increase. Who can do that? Normal force is the only force which can do that. But normal's magnitude cannot change. Normal has to balance mg. Normal's magnitude cannot change. The only thing that can change is the line of action of normal force. Okay, so as you keep on increasing this force that you apply at the top, normal force keeps shifting itself to the right. Okay, and to what maximum extent can it shift? See, normal force has to act somewhere on the base only. It cannot act outside the body. Okay, it has to act on the base. The maximum extent to which normal can shift is this much distance, not beyond that. Okay, means in this case, in this particular example, x, the distance by which normal force shifts, should be less than or equal to a by 2. Because normal cannot afford to act at a point beyond that. Okay, so x should be less than or equal to a by 2. Now here we got, for the box to be in equilibrium, we got x is equal to fa by mg, and we see that x should be less than or equal to a by 2. Now cancel a. That means the force you apply should be less than or equal to mg by 2. You apply force any greater than this, the box or the water bottle. Okay, I should not say water bottle. You apply any force greater than this box cannot be in equilibrium. If it doesn't slide also, it will rotate. It will topple. Okay, so this is what we call toppling. This is a condition for toppling. As the force applied becomes stronger and stronger, friction also becomes stronger. Assuming sufficient friction is available, friction also becomes stronger. Clockwise torque increases. For the box to remain in equilibrium, anti-clockwise torque has to increase, and which is produced by normal force in this case. For torque due to normal force to increase, normal force has to shift its line of action. But there is a limit up to which it can shift. So there is a limit up to which you can apply a force such that the box does not topple. If you exceed that limit, the box will definitely topple. Okay. Let's solve another problem based on this. Okay, just a moment. Okay, assume there is a tall box like this time. Let's say the width is A and the height is 2A. Okay. When we don't apply any additional forces, weight and normal force balance, normal force will be uniformly distributed on the base, line of action will pass through the center. Suppose you start applying forces on it, and where are you applying the force? This is the center. Okay, let's apply the force at the top itself. Next question, I'll give you a different situation. Fine. I want you to find out how much maximum force can be applied in this manner such that the box does not topple. Try. I'll give you all 2 minutes. What is the maximum value of F such that the box does not topple? You can take mass of the box to be M. Answer should be in terms of mg. Yeah. Right. I got 2 answers, one as mg, the other as mg by 4. Let's see. So first thing to do is write equilibrium condition. Now, weight will definitely be acting. Along with weight, normal force will be acting. We don't exactly know the line of action of normal force yet. Definitely there will be an uneven distribution of normal on the base. The force we are applying is to the right, so friction acts to the left. Friction has to act on the base itself. And those two should balance. Small f should be capital F, should be equal to capital F. And see, we want the maximum force we can apply such that the box does not topple. So we have to visualize the situation where it is just about to topple. And when it is just about to topple, the line of action of normal force will be along the edge of the box, like this. So you just have to write equilibrium condition with these forces. Now, net force 0 we have already considered. That is how we are able to say small f is capital F and n is equal to mg. Horizontal equilibrium, vertical equilibrium. Now net torque is 0 is the equation we have to write. Friction produces clockwise torque. Applied force produces clockwise torque. Normal produces anti-clockwise torque. So clockwise torque is equal to anti-clockwise torque if we write. Height of the box is 2a. So line of action of capital F will be at a distance a from the center. So capital F A plus friction torque small f A should be balanced by normal forces torque. Normal force multiplied with a by 2. Normal force has shifted to the maximum possible extent. Okay, that distance is a by 2. That's all. Now small f capital F are equal. Normal force is mg. So 2fa is equal to mg a by 2. A cancels, you get F is equal to mg by 4. Once the applied force exceeds that value, the box will topple. Even if it doesn't slide, it will topple. And see, it is important that the object does not slide, because we are writing small f is equal to capital F. Now, if they are balanced, that means the object will not translate. It will rotate. Okay. And about which axis does it rotate? It rotates about this axis. Okay. In fact, you can solve this problem this way also. You can take this as the axis, because you know that when it topples, that becomes the axis of rotation. Okay, that edge of the box becomes the axis of rotation. Now, assume normal has shifted to the maximum possible extent. It can't shift anymore. Now, if it has shifted to the maximum possible extent, normal's line of action will pass through that axis. It can't produce a torque. But you look at the other forces. Now, about that axis, friction also cannot produce torque, because friction's line of action also passes through that axis. Friction can't produce, normal can't produce. Mg and capital F are the only forces producing torque. Okay. How far is mg's line of action from that axis? A by 2. How far is capital F's line of action from that axis? 2a. That's all. Capital F into 2a. Okay. The torque produced by capital F should be mg into a by 2. Torque produced by mg. That way also you'll get capital F is equal to mg by 4. So whether you write about the center or about the axis around which it is going to topple, any equation will give you the same answer. Okay, next situation. Just a moment. Fine. Here also, let us take an extended box. Just a moment. Fine. Consider something like this. See, had the surface been horizontal, this box would not have had a chance to topple unless some other force acts on it. But as we tilt the surface, fine, as we increase the angle of inclination, even if the surface is rough, okay, not even enough, even if, imagine the surface to be rough enough, so sliding of the box is not going to happen. But as you tilt the box, what will happen? At a particular angle, it will start toppling. It will fall off. Okay. Find out or derive the maximum angle up to which the surface can be tilted. Okay. Dimensions of the box, this side is A, this side is 2A. Mass is M. Friction is sufficient to prevent slipping. So the box is not going to slide down. But at one angle, you know it will topple and fall. Find out the maximum angle up to which you can tilt the surface. And again, we are talking about maximum angle at which it just doesn't fall. So you have to imagine it about to fall, being about to fall. Okay. Accordingly, you draw the forces, write equilibrium condition, you'll get the answer. Try this, all of you. Okay. Assume the block is about to topple. Can any of you tell me which way it is going to fall? Like which way is it going to topple? Clockwise, anti-clockwise? I just want to know if you are able to visualize it falling or not.
Clockwise.
Clockwise. Okay. Now, if it is about to fall clockwise, just a moment. What is going to happen is this. Okay. Some points of the object are not some point. Most points of the base are going to lose contact. Fine. On the upper side. On the lower side, there will be, what do you say, more normal force acting. So, before it has toppled also, you know that like there is some imbalance here, definitely. The normal force will not be passing through the center. Line of action of normal force won't be passing through the center. Let's consider the other forces first, then you'll understand clearly. Weight always acts through the center of gravity. You can't change that. Its line of action is vertical. Okay. It cannot produce any torque about the center also. That's fine. What other forces act? Sliding is being prevented, so friction must be acting. Friction should act up the incline. It also has to act on the base itself. Where else can friction act? So this is the line of action of friction. And friction should be balancing mg sine theta here. So small f is equal to mg sine theta. We didn't apply any additional force. Okay. Now mg cannot produce a torque about the center. Friction can produce a torque about the center and it produces clockwise torque. Now we want the maximum angle for which the box does not topple. Then there should be some other force producing anti-clockwise torque. And the only force which can do that is normal. So here also the distribution of normal forces, even before the box topples, will be like this. More normal force on the lower side. Okay. As a result, the line of action of normal will shift downwards. Okay. So at one instant, it may be not at one instant actually. You can imagine it shifting here. As you increase the angle, the line of action of normal force shifts further down. And finally, when it is just about to topple, this will be the line of action of normal force. All the normal force will be acting only along that edge. Okay. And how much normal force will be acting in this case? Normal force should balance mg cos theta. Perpendicular to the incline, there should be equilibrium. That's all. We have balanced the forces. We should now balance the torques. Now, what's the maximum extent to which normal shifts? A by 2. This line of action will be at a distance a by 2. Friction's line of action is at a distance a from the center. That's all. Balancing torques. Small f, friction multiplied with a, should be normal force multiplied with a by 2. Friction is how much? Mg sine theta into a. Should be equal to mg cos theta into a by 2. A cancels, mg cancels, you get tan theta is equal to 1 by 2. It depends on the dimensions of the box, okay? Here we have taken a box whose height is twice the width, and the answer is tan theta is equal to half, or theta is tan inverse 1 by 2. Okay. Next, okay, you all can note this down if you want. I'll take another diagram, just a moment. Fine. Next situation. Assume there is a rectangular slab, okay, slab made of stone. It is placed on a rough horizontal surface. The slab's height is significant, okay? Height you can assume is a few centimeters, like maybe 10 centimeters or so. And the length is maybe 50, 60 centimeters. It's like that. You give the slab an initial velocity to the right and release. One of you tell me what forces act on it after we release it.
So normal and
Normal and
its weight.
that's all. It's a rough surface. It's sliding on a rough surface, so friction will also act. Okay. Now see, friction's line of action is obvious. It should be parallel to the surface of contact. Friction acts like this. This time friction doesn't have to balance anything. It will slow down the object. It's an unbalanced force acting on this object. Mg's line of action, has to pass through the center of gravity. Okay. Now, this is not a case of toppling. This slab is not going to topple, but from everyday experience, we know it will slow down and stop because it's sliding on a rough surface. Okay. Now you all tell me, think a little, use your own imagination and tell. How will normal force be acting? Will normal force be distributed uniformly on the base like this? Or will it tilt to one side? Will the normal forces on one side be stronger? Think carefully and answer. I'll give you 2 minutes. Okay, I got one answer as normal force will be shifted to the right. Vanilla, can you justify your answer?
When produces unbalanced torque, that's why
Okay,
normal
correct.
systems.
That's all. That's all. About the center, if you see, we know this slab is not going to rotate. Okay, but about the center, if you see, friction's line of action doesn't pass through it. It produces a clockwise torque. There should be something producing an anti-clockwise torque then to prevent rotation. And the only thing which can do that is normal force. So normal force on the base won't be uniformly distributed like this. They will be weaker on the left side and stronger on the right side. This way. Okay, so the effective line of action of normal will be shifted to the right. And by writing net torque equal to 0, like you should know how much friction acts on it. Kinetic friction, you know the formula, F is equal to mu k into n. And if the dimensions are given, you can write how much clockwise torque friction produces, balance it or equate it to anti-clockwise torque produced by normal. You can tell the distance by which normal shifts also. Okay. Fine. That is all there is in shift in line of action of normal and toppling. Just practice some problems based on this. That will be the end of this chapter. Tomorrow onwards, we'll start next chapter, gravitation. Okay. Thank you all. We'll continue tomorrow.